in today's probabilistic machine learning. So let me just recap of what you probably have been learning up until now. So variation inference is what I'm going to teach in this 2-hour lecture. And first of all, what happens is that in variation inference, we are probably talking about Bayesian inference in the first thing. So whenever we talk about probabilistic machine learning, we typically tend to think about Bayesian inference because that is the most principled way of inferring a lot of things that are usually unknown at the start. And so here is basically a probabilistic pipeline, which is basically, I often use this pipeline to describe what really is happening when you actually take up a problem. So this probabilistic pipeline, what it says is that when, let's say, if you are a company or if you are just a student who's looking at a problem, typically you look at some data and you want to infer something from the data. And so there would be some knowledge that is already present with you for regarding the thing that you are interested in inferring. And you might also have some idea of how to model this so-called unknown thing for which you have some partial knowledge, and then relate it to the data that you're observing. Okay. And so there, that is exactly where you kind of make these model assumptions. So you have some knowledge. So let's say if one is interested in a climate forecasting, thinking about what is going to be tomorrow's weather. So you have some knowledge that you probably have a good enough climate model, climate forecasting model that forecast whether there's going to be rain or not tomorrow, or if there is rain, how much would be the rain tomorrow. So you have a question that how much is going to be the rain tomorrow, and you have the knowledge that usually the rain depends upon humidity, temperature, and a few other local wind conditions. So that would actually come into the knowledge. And you would actually also bring out the knowledge of how these factors, let's say the wind speed, humidity, temperature, and many other things, how do you have a question? So how do these factors actually relate to the output that you are going to be measuring? Okay, so we're actually going to have some amount of data. We're going to be having some data, and in the case of machine learning, we have a lot of massive data. So before I progress, can I actually ask if whatever annotations I'm actually making to the screen, is it visible to most of you? Or if someone can answer yes. Are you able to see my screen when I'm making the annotations? Hello?
Yes, sir, we can.
Okay, great. Thank you so much. So as I was telling that we will always have some amount of knowledge, and this knowledge is mathematically posed as some important factors that affect your outputs that you actually can measure using some kind of sensors, right? And then you have a model for it. So I might be a company which is interested in, let's say, climate forecasting, or maybe it's a financial stock price forecasting. There could be many problems where we actually forecast and we're interested in knowing what is going to be happening the day later or something of that sort. And we will have a model for it. And you probably have been introduced to linear models, linear regression models, logistic regression models. These are all linear models. These are also kind of an assumption. You can even go for higher nonlinear models. So these are come into model assumptions. So you have some data, and you also have the knowledge of what factors relate to the data and in what way. The way these factors affect the output, that is going to be called as a model. Whereas these factors, let's say these factors are now called as Z. So I call these factors as Z, which are, you can think of these factors as factors which are not directly measured by some sensors. Okay, and therefore they're called hidden or latent variables. Okay, so in statistics or in machine learning, they're called hidden or latent variables because these are variables that are there in your model, but for which you do not have measurements. Okay, there are no sensor measurements. Then there are also certain other variables in your model for which you have measurements. And typically for those things, we call them as outputs or output variables. We call them as output variables. Now, what do we do next? Well, we have right now put whatever knowledge we had into a model. We have created a graph that shows how is the output related to the hidden variables, which I cannot directly observe using sensors. So here is kind of this actually is called a probabilistic graphical model in computer science. So this is a very, very small computation graphical model that I have created, but there are many, many. So you can actually create many, many things, X, Y, Z, A, and you can say that X affects Y affects Z, Y affects also A, Z also affects A. So you can actually create a network of graphical models. You can imagine that if you are on a social media, your friends and how you're connected to them is also forming a graphical model. Okay. Typically, in the case of uh, scientific models, we have models which are typically one direction, meaning that these arrows only move from one direction to another direction. Okay. On the other hand, in examples of, let's say, where you have the case of social media, where you actually are thinking of connections between different groups of people, then you have a bidirectional connection. Means that X and Y, they are both friends, so they can actually message each other. But X cannot directly message, let's say, Z because they are not connected. Okay, you can think of it that way. But in most scientific models, we typically have one directional relation, and therefore we call it as a causal relation. So it's one directional. So one thing affects the other does not affect these typically relations like this. So right now we have here, based on our knowledge and our question that we are interested in asking or knowing and the answer for, we can create a model, and that model effectively is basically that it will have some hidden variables or latent variables which you want to know about, but you cannot know them directly because you do not have measurements for them. Instead, you have measurement for some other variables which are called output variables. And for these variables, you can directly measure. And for these, in the case of machine learning, you have massive data for these variables, which are represented by X. And I'll right away clarify that when I write these X, this I would actually mean as a scalar. When I write this as X with an underline, I would mean this as a vector. So since I'm going to write it in a handwritten form, I will not be able to show these as vectors or scalars. So therefore, I put this underline to show that this is a vector. Okay, if I were to put double underline, this would probably mean a matrix, and so on. So in this lecture, we will only be needing up to vectors. So what we do is that we have massive data, and this massive data, when I say it's massive, which means that this particular vector X is really, really large, in the order of millions and thousands, like billions, depending upon the application that you're looking at. It's really, really large. And what do you want to do with this data? Well, you want to infer some patterns from this data. Now, what patterns you are interested in inferring, that depends upon your application. Okay. So let's say if I were taking a climate model, then I'm probably interested in knowing that what affected the rain in the last 30 years, which factors affected the rain in the last 30 years. So my output would be the rainfall of the last 30 years for every season or for every monsoon. And I would try to know that what factors actually really caused that affected those rainfall, and not only those factors, but in what way those factors were affecting. So those factors could be coming under the latent variables for which I did not have a direct measurement. I had only measured the rainfall, and I would want to infer these Z, the latent variables, which I am not able to observe directly using sensors. And once I have observed these latent variables, let's say once I've actually inferred, sorry, not observed, but inferred these latent variables from this massive data, then the next task would be that my model would be complete, or I would say the model calibration would be complete, and I would be able to kind of predict using that model for next days or next monsoon's rainfall. So this latent variable Z also appears to be in the form of something called as parameters. So whenever you choose a model, it will have its own parameters. So let's say if you are using a linear regression model, then the parameters would be the coefficients of that linear regression model. Similarly, if you're using a logistic regression model, you also have parameters of the logistic regression model. So these hidden variables Z that I denote here can actually also mean they are parameters. which means that you have chosen a model, but you are not sure of your parameters. And therefore, you want to use the data to kind of calibrate your model. Okay. Now, the question is, how do you do this? How do you actually do this in a Bayesian paradigm or in a probabilistic paradigm? Now, in a probabilistic paradigm, there are many different paradigms, out of which the Bayesian paradigm, which is based on the famous rule given by Thomas Bayes, is this Bayes rule. So the Bayes rule says that if you want to infer this parameter or this hidden variable z, so this is the hidden variable z, okay, and we are interested hidden, or it's also called as latent variable. You are interested in actually finding or inferring this latent variable given these measurements. So then Bayes rule says that you have to find out what is the probability of the variable, a joint probability of the variable z given the data. So that is given by this Bayes rule, which is the probability of the data given the variable z multiplied by the probability of the variable z divided by the probability of x, the data. Now, I believe that you have already seen this Bayes rule a couple of times in the last 2-3 days. And I just want to recap here that this probability P of Z here denotes the prior probability over the latent variables, which means that what do you think is going to be the distribution of this of over these latent variables before you have seen any data. So it is much like asking the question that if I were to ask you that, can you give me an estimate of the rainfall for, let's say, this monsoon, you would probably be having a model, but you really don't know what parameter values to be put there. And if I force you to kind of make a prediction, you will put some parameters which are based on the best guess that you can provide, right? So the best guess that you can provide is kind of, you can think of that as a prior. Now here, it is not a point estimate, okay? The parameters here are not just a point estimate, but rather here there is a probability distribution over the parameters, okay? It is much like asking that if you are to a new place, and if you are going to take a bus from a bus stop, then you go there, you have never taken a bus from a bus stop there, and you go there with a feeling that, okay, it's written that the bus is going to come, let's say at 8:30, but once you arrive at the bus stop, you have a distribution in your mind that, okay, the bus is going to come maybe on an average around 8:30, but it may come a little bit late, it may come actually maybe it come much later. The probability of the bus coming much later than 15 minutes is very less. So you actually, in your mind, you have a probability distribution of when the bus is probably going to come. Okay, so maybe this is where it is 8:30, and as it is going further, the probability reduces, and it also has a very small probability of coming earlier than 8:30. Okay, so you are actually forming a probability distribution in your mind about when the bus is going to come, right? So then, so you can think of that, that's called the prior probability. Before you have actually seen the bus come, you are just thinking that when is going to be the time, and that is called a prior probability. As the name suggests, prior, meaning that knowledge that you have before you have seen anything. That's a prior knowledge. And then you have the likelihood, which is basically the probability of the observations given that your prior knowledge. So now that you have, let's say, a prior knowledge, you believe that in India buses usually would come late. You found that yes, indeed the bus came late, and it bus came 7 minutes late, let's say. So then you will say that you maybe in your mind thought that it would come 2 minutes late, but the bus came 7 minutes late. So based on your model that the bus would have come 2 minutes late, the bus actually came 7 minutes late. So what is the probability that the bus would have come 7 minutes late, given that you had assumed that it would come 2 minutes late? So that is actually what is called the calculation of likelihood. Okay, like this, you can actually calculate for various values of x for like several, it need not be 7 minutes, it could be like 5 minutes. You can actually observe as many, and depending upon that, you can calculate your likelihood, right? Now, what is the point? The point is you want to be knowing later on, after you have seen several times that the buses come this late, you are going to be forming an impression in your mind. What is that impression? That impression is that the bus usually comes 7 to 8 minutes late at that bus stop. So probably I would want to make a decision that I would probably never arrive early. It's okay to arrive 2 minutes late, but I have found on an average that the bus comes 7 to 8 minutes late. And that thought, that impression that you have actually got after having seen the buses come late mostly, that impression is called the posterior. So that represents your posterior knowledge, a knowledge which you have acquired after having seen the data. Okay. So you see that Bayes rule is a very important rule which connects that how do you update your belief about a certain thing based on a prior belief about that thing times the observations coming in the form of likelihood. Okay. And those two, the top two, are multiplied with each other, and then it is divided by something called, which is called the evidence or the marginal. Okay. So this is called the probability of the data, because X here represent the output variables, which means that they are also the data that we collect using, let's say, sensors. And the probability of the data is called the evidence, and that is nothing but a constant. Once the data is there, the probability is going to be fixed because the data has been gathered. There is no amount of things which are unknown right now. You have gathered data, and that data is now going to be. So this evidence is a fixed quantity. Unfortunately, is there in the denominator. And this evidence creates a massive problem in applied Bayesian inference. So Bayesian inference, all this Bayes rule seems very nice, but when you are about to do the calculations, the computations, the real computations, when you actually were to write code, then you will find that this is the term that actually creates a nuisance. Because how do you calculate this term? How do you calculate the probability of this data? You have the data, but how do you calculate the probability of the data? That is not clear. Okay. And this is actually a nuisance term, and you probably have already seen a couple of lectures where it was shown that since this particular term is not very easy to handle, therefore we tend to find out this posterior using different other techniques. Okay, one of the techniques that you have already seen is MCMC. So just to recap here, I'm just going to give you again a broader idea that the oftentimes our question is that we have some knowledge about our about the question that about the answer to the question that we're going to ask, and that knowledge is either represented through a model where there are some hidden variables or latent variables that you are not able to directly measure, and those hidden variables are connected to the output variables in a certain form which you already know, and these output variables are actually obtained using sensors. And let's say you have massive amount of data collected continuously from those sensors, and you gather that data, and now your idea is to infer from the data what are these patterns or what are these hidden variables that you did not know. You want to know about them, and once you know about them, then you can use the model for prediction later on. So that's the question that we are interested in asking, and therefore in Bayesian inference that answer is actually given by this posterior. So this posterior is very important. This posterior is a very important probability distribution that gives you what is the probability of the latent variables given that you have now seen the data. So it's an updated belief. And posterior inference, as I write here, is a key task in Bayesian inference. It answers the question that what does this model say about the data? So you have now gathered the data, you have chosen a model, and you are trying to ask using the data, what does the model say about the data? What does your model say about the data that you want, the model that you have chosen? So in probabilistic machine learning, the way it works is like this, that we actually create a probabilistic model, which is nothing but a joint distribution. It's a joint distribution of hidden or latent variables, Z, and the observed variables, X. So as I was telling you that the hidden variable, which is Z, I'm going to put an underline because that's a vector. Hidden variable, which is Z, is affecting the output variable. Okay. And the probabilistic model that connects these two are going to be the joint distribution. The joint distribution, which I'm going to write it as probability of X and Z. Now here, I'll often assume that the joint distribution actually means the joint density. So you know that in probability, there are two functions. One is the probability distribution function and the probability density function. The probability density function is nothing but the derivative of the probability distribution function if the derivative exists. Okay, but almost most of the cases where we work, those kind of distributions do have derivatives. So therefore, I'll assume that the density functions and the distribution functions, whenever I use, they are interchangeable. Okay, mostly I actually would mean by distribution, I would mean the density function. Okay. Now, in probabilistic machine learning, a probabilistic model is basically a model which is a joint distribution of the latent variable. This is the latent variable and the output variable or the observed variable. You can also call it as the observed variable. Okay. And what are we interested in? We are interested in inferring the unknown hidden variable z through the posterior. And what is that posterior? We have already written from the Bayes rule. The posterior is like this. Posterior is z given x. Z is the unknown variable that we are interested in, the hidden variable. X is our data, and that, according to the Bayes rule, is actually given as a likelihood of the data, which is x, given the hidden variable z, times the prior probability over the hidden variable, divided by this denominator, which is kind of a nuisance term. As I told you, this is a nuisance term, this denominator here. And here I'm going to write it also like this, that the top term here, this top term here, okay, this top term can also be written as a joint distribution that I have already defined here. This is a joint distribution that I've already defined. And you know that by multiplication rule, this is the multiplication rule. You can also write this as probability of x comma z divided by p of x, right? So this thing actually is nothing but it is decomposed into the likelihood and the prior, right? So we want to infer, our goal is to infer this probability distribution, which is the posterior probability distribution. Now, as I've told you that you have probably seen that this particular denominator is actually a nuisance. Why is it a nuisance? Well, in papers and books, it will be said it is not tractable. It is not tractable. It took me almost one or 2 months just to understand what do papers and books really mean when they say that it is not tractable. Okay. Of course, nowadays you have chat gpt, so which you can easily ask chat gpt what is meant by tractable, and it will probably answer you. But at those times when I was doing a phd, it was not so easy to actually kind of get these answers directly. Anyway, so the idea here is that what we mean by it not being tractable is explained like this. So this p of x, which is the denominator, and it's also called as the evidence or the marginal, and this is a nuisance term. And why is it a nuisance term? Because this probability density function or distribution function, whichever I say interchangeably, is actually a multidimensional integral. It is a multidimensional integral. Okay, it's a multidimensional integral over the space of z in this particular fashion. It is, I can write it as probability of x, and then z, which is a vector, let's say I represent z as a vector, which is like z1, z2, and let's say it has m number of components. Then what you will find, I'll write here as z1, then I will write it as zm, and here I'll write it as dz1, and it goes up to dzm. And here this is an m-fold integral. This is m-fold or m-dimensional integral. So there are like these integral signs. There are m number of those. This is an m-fold integral or m-dimensional integral. You can people also call it as dimensional, m-dimensional integral. Okay. And what do we mean by it is not tractable? When we say that this denominator is not tractable, what we really mean is that this particular integral will probably not have a closed form solution. Okay, closed form an analytical expression. So to give you an example, you know how to integrate sine of z, right? Sine of z dz, you know that how to integrate that you know, because we know that there is a closed form expression of sine of z if you integrate it from like this, right? But what happens is that not all integrals have a closed form solution, and this is one of the cases when I say it is not tractable, the denominator is not tractable, this p of x, the evidence terms, not tractable means that this particular integration does not have any closed form analytical solution. Okay, so that is one problem. If you do not have a closed form analytical solution, you cannot evaluate it. Or okay, fine, if we cannot do analytical solution, can we do anything else? Yes, there is something called as numerical integration. But the problem here is that you could do a numerical integration provided that the dimension, the m, is actually small. If m is small, this z1 up to zm, if this size m is quite small, let's say less than 10, something of this sort, then you can do numerical integration quite comfortably. But if the dimensionality exceeds, which often happens in the models that machine learning deals with, for example, you can think of ChatGPT has almost close to billion parameters. Okay, so billion. Look at this number 10, and I'm talking about billion. You can imagine that the number is exceedingly large. And for such kind of cases, it is because of the dimensionality, purely because of the dimensionality, that you cannot have a numerical integration. Okay. So dimensionality is too large for numerical integration. And this is what we mean by not being tractable. By not being tractable, it means that either this particular expression cannot be obtained in the closed form, and or the dimensionality is too large for it to be actually done in a numerical integration fashion. So then what is the option? Well, the option is, you have probably seen that when you have learned about Markov chain Monte Carlo techniques, they actually avoid calculating this evidence by actually taking a ratio. By using a ratio, they actually kind of use, because this is a constant, if you take a ratio of two posterior distributions, then this evidence term will actually cancel out. And that is how they actually kind of construct a Markov chain, which eventually would actually asymptotically converge to the posterior. So what are the options available? The options is that we have to somehow get rid of this evidence term. This evidence term is creating a mess in our life. We have to get rid of it. And therefore, we have to find the posterior in some approximate way. And therefore, the idea of approximate posterior inference. Okay. So then what we do? Well, we have two schemes available to us. One is something that you have already now learned. This is called, the first one is sampling based stochastic approximation. I emphasize this idea of stochastic approximation, which are basically methods like MCMC, which we have already now seen. So what do they do? Well, their idea is, as I have already mentioned, is that they actually take a ratio of these distributions. They actually find, they have some proposal distributions using which they will actually create a ratio for this posterior. And by creating this ratio, they will actually eliminate this evidence. They will eliminate this evidence because it's a ratio. The evidence is constant, and therefore it will be eliminated. And you're going to be only working with the numerator in the ratio, two numerators in the ratio. And then they will create a Markov chain with some starting point, let's say here. So let's say this is the target distribution that we are interested in. Okay, this is the target distribution. P of z given x is the target distribution. And you want to, what we do in sampling, in sampling based stochastic approximation, we generate samples which would eventually kind of resemble the posterior. So this is the posterior, which is the target distribution. You want to be, you want to kind of know this posterior, and once you know the posterior, your goal is complete, because that is what you were after in the very first place in Bayesian inference. So you start here and you keep on sampling in the space of z. You keep on sampling like this. So here, like, you actually come here and you keep on sampling like this. So let's say this is a starting point, and you keep on sampling in a random fashion. So this is random sampling. It's a stochastic sampling. It's random. And then eventually what will happen, that once you, if you have infinite computational time, I mean theoretically at least, if you have infinite computational time, then you leave your chain to actually keep on exploring the space of z. And it is for sure that eventually, if you have enough, if you leave it for enough number of time, then this chain is supposed to converge near the target distribution, which is our posterior distribution. And what will happen is that eventually once it reaches its home, it is never going to be leaving its home, which is the target distribution. So after the samples have mostly reached the target distribution, it will actually be mostly around the target distribution. So it will generate a lot of samples from the target distribution. And using the samples, you can now create a histogram of this target distribution, which is the posterior. So this is the idea of MCMC based methods. Today in the morning, you have actually encountered HMC, Hamiltonian Monte Carlo, which is a very, very efficient way of doing, or efficient way of actually creating Markov chains which converge quite fast. But still, that quite fast, I'm saying, is also very, very computationally expensive when we're talking about probabilistic machine learning. And almost nowadays, MCMC based methods are never almost used in probabilistic machine learning. You will only find it in some research papers to do a benchmark study, but usually in practice, no company that I know actually uses this MCMC methods for doing probabilistic machine learning. So what do they do then? Well, now because of the extremely large size of your latent variables. So here you see that the latent variable size, MCMC and all this stuff you can do for variables when z, the vector z, is of, let's say, size 100, maximum 100, or I have probably never seen people go below beyond 100. Okay, so if you have your latent vector which is of size not more than 100, you would probably be able to do that MCMC. But even then, I will actually say that I have not seen many people do this. People usually have not tackled problems beyond, let's say, 10 or 15 or 20 with MCMC, because it becomes very, very costly. So what people do in machine learning these days, they actually use deterministic approximations. Okay, no more stochastic sampling, they use deterministic approximations. So what do I mean by that? Well, what was our goal? Our goal was to actually get rid of our evidence. This one, this was creating a nuisance. So let's say I'll go back a little bit here. So we were interested in finding the posterior. This is our posterior probability of the latent variables given our observations, that is the posterior. And we were to calculate this posterior, we had to get rid of this evidence. This evidence was creating a problem because it is usually not tractable. And why it is not tractable? Because it may not have a closed form solution, or if I mean, it might actually have a dimension which is very large for doing numerical integration. So that's a problem. Fine. So let's resort to approximate schemes which are deterministic in nature, not samplings, because sampling has its own problems. But let's resort to a deterministic approximation. So when I say deterministic approximation, what do we really mean? Here we mean that we will use an analytical approximation of the posterior. So let's say here, this is the posterior we have. Let's say this is a target distribution. Okay. And of course, to start with, you will not know the target distribution, which is the posterior distribution. Because if you know the posterior distribution, then your goal is already done. Then your task is already done. Your goal was to find the posterior distribution, right? And therefore, this is just for an example that I've drawn here. And this is a distribution. You can think of that this is a distribution like this. And you really don't know about this distribution from the starting. You would have to infer this distribution given the data, and therefore it is called the posterior. Now, using deterministic approximation, we will use an analytical formula or analytical distribution to actually fit it to the target distribution. So what we can do? Well, what we can do is here is that, let's say I do not know what distribution it looks like. I really do not know that what is my target distribution. I have no idea, but I feel that I do not have too much of time. I believe that I will actually take a normal distribution, and I will try to fit the normal distribution as best as possible to the target distribution. I do not know the target distribution. So the target distribution actually looks like this. Okay. But I have no idea. I want to know about the target distribution, but I do not have the computational resource to run an MCMC for finding the parameters or for finding the latent variables. I do not have that kind of a facility available with me. So what I do is that I have recently learned about these approximation techniques which are deterministic. And then what I do is that I say that, okay, I'll choose my distribution that I want to be approximating is, let's say I'm going to use my Gaussian distribution and I'm going to force my Gaussian distribution to fit the target distribution as best as possible, as best as possible. Now you see that a Gaussian distribution. So let's say if I have a Gaussian distribution, so you know that in a one dimension, the Gaussian distribution would be looking like a bell-shaped curve, right? Looking like a bell-shaped curve. Of course, the size of the bell will actually depend at whether it's going to be a very narrow bell or it's going to be a very broad bell. That depends upon the standard deviation of the bell, right? And also where it will be located, that will be given by the mean. But you can very much understand that this is a single mode distribution. It has only one mode. It has only one peak. Whereas you can clearly see this for this example, the target distribution has two peaks, right? It has two peaks, one here. By the way, this is a contour. So this is a contour. So this is a 2D plot where you are the darker the shades, the higher is the peak. So it's a contour plot. Okay. So here from the contour, you can think that there are 2 points where there is a peak. So you can think of it as a hilly region where there are two peaks. Now you can never actually kind of approximate the two peaks by a distribution which is having only one peak. That is not possible. So what best can you do? The best thing that you can do is that you can approximate one peak. Let's say you are only trying to approximate this one peak. So your now your analytical approximation or your analytical posterior, which I'm going to now call as a variational distribution. Variational distribution. The name comes as the term variational comes because of a completely different reason, because of variational calculus. But as such, even without you knowing variation calculus, it is, I mean, you can actually easily understand variation inference. The terms here, in the case of variation inference, certain terms are actually taken from different disciplines, and therefore they have names ascribed to those disciplines. But as such, you don't need to know the discipline to understand variation inference. So these kind of analytical so basically the goal was to actually approximate our posterior, and we found that the approximation to the posterior was creating a problem because the evidence was sitting in the with the denominator, and calculating that evidence was actually difficult. So MCMC kind of got rid of the evidence by doing a ratio. In deterministic approximation, we'll try to find a approximation to the posterior such that we can convert the problem of posterior inference as an optimization problem. And that is what I'm going to come to. But first thing I want to impress is that there is no free lunch. Here, we are going to give you a very fast method, but there is going to be a there is going to be a problem. The problem is that this method will never, almost never generate exact results. What do I mean by that? Well, this is the target distribution. Okay, this is the target distribution. And you can clearly see that this particular target distribution, you do not know to start with, you do not know, you want to know. And but you want to know, but you do not have the computational resource. So you are saying that I'm going to fit my own chosen family of distributions to this. And let's say if you choose a Gaussian, let's say this is a Gaussian, which has only one mode, having only one mode or one peak, right? One peak is also called as unimodal, right? It's a unimodal distribution. You will never be able to capture a, this distribution which has two peaks. This distribution which has two peaks, you will never be able to capture these two peaked distribution or bimodal distribution using a unimodal distribution. Which means that the moment you actually choose that I am going to fix what distribution I'm going to use to fit my target posterior, you have actually made a compromise already, because you really do not know how your target distribution look like, and you have already said that I'm going to fit it with only a unimodal. So you have made a compromise, and that compromise will appear in the sense that you will never ever actually fully capture this target distribution. Okay, so you will never capture this target distribution exactly. That is what I mean. Not that you cannot capture it, you will capture it with certain good amount, but not exactly. So when you actually try to capture this target distribution using your chosen variational distribution, this is, let's say, your chosen distribution, you are now trying to fit it. So you can either fit to this mode, you can either fit it here, or you can fit it to this one. Okay, because it's a unimodal, you can either fit this one, or you may actually fit it like this. Okay, you can actually fit it like this. It's trying to be kind of an average of both of them, right? So these are three different kinds of fit. We will see that in variation inference, we are going to be mostly talking about these two kinds of fit. This particular fit, what you see here, comes from something called as expectation propagation. Expectation propagation, or it's also called as belief propagation, but expectation propagation is a more correct name. I'm not going to talk about this, but I'm going to tell you how we are going to use these analytical distributions, distributions which have analytical form, to be able to calculate the posterior, or to be able to approximate the posterior. Okay, that is the talk. That is what we're going to cover in this lecture today. Now, so let's come back again and ask the question that what is the problem statement? So what do we want to do? Well, we have our model. So we have our model which is looking like this. So this is our model. This is our assumed model, which I'm showing by the use of a probabilistic graphical model, a very simple one, where I have some hidden variables or latent variables, could also be parameters of your model, and that affect in a certain way the observed variables x, and that how it affects, that is actually called your model. So in the case of linear regression, that would be your linear model. So x will be a linear function of z. In the case of nonlinear regression, x would be a nonlinear function of your model z. Okay, nonlinear function of your model parameters or the hidden variables z. Okay, so depending upon how you choose your model, that is your observed, that is your relationship. So you now know this, and the goal is that you want to find out. And again, I just emphasize that my z is actually a latent variable is actually a vector of, let's say, size m cross 1, and my observed variable is also a vector of size n cross 1. Typically n is much larger than m in the case of massive data sets, where you have a huge amount of data and there are certain number of hidden variables that you want to infer. So the goal is, so the goal here is to approximate, the goal here would be to approximate the posterior over the latent variables, over the latent or the hidden variables, latent or hidden variables, given the observed variables or given the observations. Okay, using a tractable. Now you know what it means by tractable. Okay, now using a tractable family of distributions, tractable family of probability distributions. Okay, tractable means whose analytical solution in analytical form is available, typically distributions. And these distributions we call as a variational distribution. So they're actually going to be written as q. Just to be differentiating it from p, we're going to write it as q over this latent variable z. And these distributions has its own variational parameters nu. Okay, just to give you an example, let's say if I choose my variational distribution. So here in this example, let's say if I choose my variational distribution as a normal distribution, z, then I would have parameters. The parameters of a normal distribution are what? Mean, and let's say it's variance. It's variance or covariance matrix. Okay, so if I write it as a mean, if it's mean, and then my covariance, it's a sigma matrix. Okay, so these will be here. These two things would be my variational parameters nu. I'm going to convert them into a huge vector. So mu is a vector itself. Covariance matrix, I can make it, I can actually arrange the columns of the matrix as a long vector, and I can create a vector like this. Okay, so these parameters would be called as the variational parameters. Variational parameters. And you will see that these variational parameters are the parameters that we will optimize in our variation inference. So what we really mean, the goal is actually to approximate, the goal is to approximate the posterior, the real posterior, the target distribution. This is the real posterior, which was related through Bayesian inference like this. Through the Bayes rule, it is related like this, right? And we want to be able to approximate this posterior using our variational distribution, which has its parameters nu. We want to be able to approximate it. Okay, and once again I'll write that this is the evidence and this is our model, the joint distribution. right? So how do we convert this? So we actually don't want to use sampling. Clearly, we have already chosen our variational distribution. This is our variational distribution, and we want to be able to optimize our variational parameters in such a way that our variational distribution fits the target distribution. Now, mind you, we do not know the target distribution. So how do we fit it? How do we know that our variational distribution is actually going to be a good fit to the posterior distribution? Because we do not have any idea about the posterior. And here is where the math of variation inference will actually help you understand that how do we actually, without knowing the posterior distribution, go closer to the posterior distribution using our variational family of distributions. How do we do that? And that is the basically the idea, that how do we convert this problem, which is of Bayesian inference, into an optimization problem. So the idea is to convert or to turn this inference problem, into an optimization problem. Because optimization we can do very well. You want to do it in an optimization problem. And what do we want to do in the optimization problem? We would try to minimize. We will try to minimize the difference between what and what? The difference between the analytical variational distribution that we have chosen, variational distribution, which is this one, Q of Z, whose parameters we are going to be trying to change. And this, we are going to minimize the difference between this one, the analytical variational distribution that we have now chosen, and the actual posterior, the actual or the true target distribution or the true posterior distribution, the actual posterior distribution. And what is our actual posterior distribution? That is actually given by probability of Z given X. That is exactly what I'm writing here. I want to be able to minimize the difference between my posterior distribution and my analytical distribution that I've chosen. Then the question is that how do you do that? How do you do that? So basically, okay, we have 2 points. I know that key I can, if I how do I say that the 2 points are different? I can take a different, I can find out the distance between this. Let's say the mean square distance, and I can say that if the mean square distance is not 0, then there is a difference between the 2 points, right? That I can say. But how do I actually say the difference between two distributions? Well, one way to do this is actually to use. So therefore, the question that how do we minimize the difference between the analytical distribution Q of Z and the actual posterior distribution Pz of given X? We have to define some metric based on which we can say that, okay, if this metric is given this value, then that is actually better than this one. So we have to define some metric, much like we have for prediction, we have, let's say, a root mean squared error, by which we can say that the error is this much and error is actually lower than this one. So based on this, we also kind of have to develop a metric based on which we will actually kind of create an optimization problem. Mind you that we want to convert that this inference problem into an optimization problem. In any optimization problem, you have to have some kind of objective function that you either want to minimize or maximize, right? And here the goal is that we want to kind of create a analytical distribution that becomes closer to the posterior distribution. And this idea of closeness has to be described mathematically, right? We have to define this idea of closeness mathematically. So that idea is actually given by a metric called Kullback-Leibler divergence. So the metric that we will use is called Kullback-Leibler divergence. It's also called as KL divergence. Okay. Now, let's first see that what is this divergence? What is this KL divergence? So the question, what is KL divergence? Have we heard about it? No, probably we have not. What is it then? So KL divergence is effectively a measure of information that quantifies how dissimilar two probability distributions are. So I'll just write that down. It's a measure of information that quantifies, or that quantifies how dissimilar a probability distribution, let's say P of X, just write it with a different color. Let's say P of X is a probability distribution. It could also be a vector, over a vector. How is this distribution dissimilar to another probability distribution? Measure of information that quantifies how dissimilar a probability distribution is to another probability distribution. Let's say that is Q of X. Okay. How is P of X different from Q of X? Okay. So that is, I'm going to write out the mathematical form, but we have this property that KLD, which is a short form of Kullback-Leibler divergence, is always a positive, a non-zero, a non-negative quantity. It's always non-negative, means that KLD is always greater than or equal to 0. And the KLD, or Kullback-Leibler divergence, between two distributions is only equal to 0, meaning if it is equal to 0, it means that P of X, the two distributions P of X, are actually same, right? So it's much like that mean squared error. If the mean squared error is 0, it means that your prediction and your data is actually exactly matching, and therefore you will have mean squared error equal to 0. So here KLD is a positive quantity. I mean, it's non-negative quantity, and it can become 0 only if the two distributions, they're exactly same. So if that, because it measures how dissimilar a probability distribution is to another, therefore if they are same, then it is actually equal to 0. Now mind you, I'll actually put a note here that KL divergence is not the same as KL divergence is not the same is KL divergence is not a distance metric. It is not a distance metric. And why I want to say this is because a distance metric is symmetric. The distance of point A to point B is equal to the distance from point B to point A. Okay, the distance between, let's say, Delhi to Jaipur and from Jaipur to Delhi has to be the same. Okay, and that is why it's called a symmetric matrix, the distance. Whereas a divergence is not symmetric, it is asymmetric, meaning that the divergence between the distribution P to Q is not the same as the divergence between the distribution Q to P. Okay, and an intuitive understanding of a KL divergence is something like this. You can think of that if I want to make my distribution P look like Q, then how do I need to massage it so that it will actually look like distribution Q? The way I need to massage distribution P to look like Q is not the same way that I need to massage distribution Q to look like P. And that's the essential idea of KL divergence, that it is in that way. How will you actually change a distribution to make it look like the other distribution? So therefore the idea of divergence, and therefore also the idea that when you define KL divergence, you have to say which distribution you're going to massage to get to where. Okay, so here there is this idea called forward KL divergence. I'll use this one, this color, forward KL, forward KL divergence, where you are defining, let's say if you have continuous variables, then you are defining KL divergence over two variables, over two distributions P of X and Q of X. So this is how we actually denote in KL divergence. Okay, KL of P given Q, P with respect to Q. Okay, like this. So this is called forward KL, and you are going to write it like this for a continuous distribution P of X. It is defined like this: P of X, Q of X dx. So this is a definition of a KL divergence. Okay, this is a definition of a KL divergence. Now this is how the KL divergence of P with respect to Q is defined. Okay, now the question here is that you might have already seen how we define expectations over a random variable, over a functions of a random variable. So we have, let's say, if I remind you that expected value of, let's say, a random variable x, or let's say a random variable g of x, Okay, and x is actually distributed according to some probability distribution p of x, and that was defined as integration of g of x p of x dx. That is the definition of an expectation over a function of a random variable. So here the random variable here is x. This is the random variable. Okay, and that random variable is actually having a probability distribution which is like this, which is this is the probability of the probability distribution of the random variable, and you are interested in finding the expected value of a function g of x of this random variable. Okay, so that's the expected value like this. That's the definition. Why I introduce this definition, you'll be you'll follow that right away here, that you can see that here this particular integral, so you can see that expectations are integrals, right? So here if you look into this integral, you will see that this is an integral of a function. This is the function. Okay, this is a function, you can think of g of x, and this is the probability distribution over x, which is the p of x part, and this is d of x, right? So again I have missed a underline, d of x. So if you understand this, then you will quickly realize that this is nothing but expected value, right? Expected value of log of p of x over q of x, right? This is expected value. And just to be sure about with respect to which distribution this expectation is taken, we are going to write it as p of x. Okay, so this expectation is taken with respect to p of x, which means that if you were able to generate samples from p of x, if you were able to generate samples, so this is here, if you can generate samples from the distribution of p of x, then you can evaluate this expectation using Monte Carlo integration. So the moment I write it here as a p of x, I want to really make you understand that x, you can sample x from the distribution p of x, and this is going to be important. Okay, you'll see that quickly this is going to be important. Now, what is our goal in variational distribution? Our goal in variational distribution is to select an approximate probability distribution, which is our variational probability distribution q of z, from a family of distributions which have analytical form. Analytical form, let's say I'll give you an example of analytical a distribution which is analytical form. Let's say Gaussian. Everyone knows how the what is the analytical form of a Gaussian distribution, right? We know that. And let's say if I write uh, x is actually a distributed as a Gaussian random variable with mean mu and let's say sigma square as the variance, then I know that x is actually having a distribution x, the probability of x is going to be equals to 1 over square root 2 pi. I know the form. So this is the analytical form, right? Exponential of x minus mu square divided by 2 sigma square, right? Minus of it. So I know this analytical form. So that is exactly what I mean by analytical probability distribution, meaning that whose forms I know. In fact, I will also go a little bit further. These are also distributions from where I can sample. I can not only not only do I know the form, but I can also sample variables from it. You can generate a random sample of a from a normal distribution by using, let's say in MATLAB randn. Okay, so these are analytical tractable analytical probability distributions. So we choose a family of distributions. Let's say there are many families of distributions which are analytical. Normal distributions are one of them. There are also others like gamma distributions, uniform distributions. There are many other distributions. So you choose a family. Let's say if you choose a normal family, then you have a family of normal distributions. Okay, and what you do that you choose in your variation, you choose your approximate probability, you choose a family of distributions which you want to kind of optimize. You have to choose the family of analytical distributions, and from that one particular member will actually kind of optimize in such a fashion that your that optimized distribution, variation distribution, will be closer to the posterior distribution. So the goal here is that you have to kind of tweak. So you can think of it, when I say it is a family, what do I mean by family? Family means that let's say if you choose a normal distribution, the normal distribution, there can be many distributions which are actually normal distribution. A normal distribution, let's say if your actual posterior distribution looked like a red curve, this red curve that you actually see behind this red curve here, this red curve actually shows, let's say, the true posterior probability distribution that you have no idea about. Okay, and what you are trying to do is that you are trying to fit your variational posterior distribution, which is you have taken to be a Gaussian distribution or a normal distribution, and you are actually creating that from that family of normal distribution, you are seeing that which one actually fits the posterior distribution the best. You can clearly see that this is one normal distribution 5, 0.1, which is quite further away from the the posterior. This is the posterior. Okay, so let me just highlight, this is the posterior. Okay, so the posterior distribution is shown in red, and the blue ones are some candidate variational distributions coming from a family of Gaussians. Okay, family of Gaussians. You can see that this blue one, is actually not doing well at all, because it is very far away from the red posterior distribution. So that is actually not a good choice. This one, here is also not a very good choice, because that is also a little bit far away, but still is better than this one. Then there is another one which is like this, right? That is also not great, because it actually spreads too, it spreads itself too thin, right? So that is also not best. Probably this one here is actually at least better, because the target distribution, you see, it has a multimodal peak, and you have chosen your analytical distribution to be Gaussian, which has only one peak, which means that you can only do so much, right? So effectively what you see is that you are just playing around with your parameters. So every parameter value that you choose is going to give you a particular relation of your distribution, and therefore the idea of family of distribution. So you can see that all these blue Gaussians belong to the same family of Gaussians, right? So you have chosen a family, and then you're trying to find which particular distribution having a certain value of its parameters as mean and, let's say, standard deviation, is going to fit the my posterior well. That is the goal in doing this scale divergence. So scale divergence, actually we introduce scale divergence from the idea that we are going to say that we are going to find out our probability, we are going to fit our approximate distribution in such a way that the scale divergence between the posterior and my distribution is going to reduce, because now I have created a metric to assess how far is my distribution to the posterior distribution. Okay, so I'll actually recap that. So here the goal then becomes the goal. So we are trying to reduce the posterior inference problem as an optimization problem, and for the optimization problem we have to create an objective function. The objective function is now being set. So the objective function then is that we have to reduce this scale divergence. So the scale divergence we have to reduce between what and what? The scale divergence we have to reduce, let's say, between my target posterior and my approximate distribution. That is, I'm trying my approximating distribution. So this is my distribution which I'm trying to use to actually kind of capture my posterior, which I don't know in the very first place. And I have now defined my scale divergence, which I'm going to kind of use as a metric to judge how should I tune my parameters of my variational distribution, or my variation parameters. How should I tune my variation parameters such that my scale divergence reduces? That is my goal. Okay, so therefore the variational distribution that actually minimizes, or rather I will say that the variational parameters, these are my variational parameters. These variation parameters, which I mean the optimized variation parameters will give me the optimized variational distribution, and that is basically obtained by reducing the scale divergence between my posterior and my target posterior and my approximating distribution, which is a variational distribution, right? So the question now is that we have now created our objective function, right? Our objective function is created, and we have to only see that can we find out this objective function. We have now created a metric, but can we evaluate this metric? It turns out no, we cannot evaluate this metric. Why can't we not evaluate this metric? Well, the problem is because this metric scale divergence that we have now defined, this particular here, let's write it out, that how did we define the scale divergence. It is actually defined like this. Here it is defined as the expected value, and here you see that, I'll just go back here. When we wrote out this, let me just rub this out here. So here when we wrote this out, we showed that the scale divergence between px and qx is defined like this, where the expectation will come out in terms of p of x. expectation will come out in terms of P of X, right? Now, when we actually substitute P of X as P of X, P of Z given X, then what will happen? This particular distribution will become probability of Z given X. And that is exactly where we face the problem. You see that all this was fine. We have defined our objective. We were getting slowly closer to our goal. And suddenly something happened and we are feeling again a little bit lost. Why? Because here you'll see that this expected value is going to be calculated with respect to the posterior distribution, right? That is going to be calculated with respect to the posterior distribution. And here inside, you will have log of P of Z given X, and then that divided by Q of Z. Now, where is the problem? The problem is that this particular distribution here, which is the posterior distribution, right? This is the posterior distribution. This is our target. We do not really know. We don't know this yet. And not only that, we need to also sample from it. Not only this, not only do we need to know the posterior, but we also need to be able to sample from it. So that's the problem. This posterior is actually unknown, and we do not even know if we will be able to sample from it. Okay. So therefore, we are stuck with this objective function. And so we say that now that this is a problem and we want to kind of avoid this problem. So an alternative is to use the reverse KL divergence. So as I told you that KL divergence is a divergence, it is not a distance. A distance is symmetric, meaning that the distance from point A to point B is same as a distance from point B to point A. But that is distance and not divergence. Divergence is not the same. So now what we will do is that we will introduce the reverse KL divergence. What is the reverse KL divergence? Well, it is the KL divergence of the distribution Q of Z with respect to P of Z given X. Okay, it is a reverse. So if you want to see that what is the difference between the forward and the KL, so this is the forward KL, this is the forward KLD, and this is the reverse KLD. And you will see that the difference is that here in the forward KLD, you are actually kind of finding the how to massage P of Z given X to actually go to Q. And here we're actually looking at how to massage Q of Z to actually make it go to P of Z given X. Okay. So here, what easy thing that we actually, that the convenience of this reverse scale divergence is that now if you want to minimize this reverse scale divergence is actually defined as expected value of with respect to Q of Z. And here I'm going to write as log of Q of Z given probability of Z given X. Now we get two convenience. One convenience is that this particular thing is tractable, analytically tractable. We know the analytical form. And not only that, we will actually choose them to so that we can also sample from it. So tractable means we know the form. We know the form and we can also sample from it. Okay. Okay. So great. We have actually overcome one difficulty that we are going to be using the reverse QL difference. So now our objective is now changed argument minimum again QZ of Q, and this is going to give us our variational distribution Q of Z. Okay, this is all fine. We have now redefined our objective to make our life a little bit easier. But again, the question comes that are we able to kind of still do it? Okay, are we able to still kind of get to a point where we can do the computation? We'll see that not yet. So before that, let's just recap once again so that you don't get lost. We have defined our latent variables. We have defined the map of the latent variables to the observed variables through a model. Our goal was to find out the posterior probability of Z given X, right? That is actually given like this. But this inference, this posterior inference is difficult because this marginal here, this marginal or the evidence term here is actually the culprit. It's very difficult to calculate. We want to be in variation inference. We want to convert this into an optimization problem, where we choose a variational distribution that is analytically tractable, mean that we can actually get the closed form expression, and we can also sample from it. We take those kind of a distribution and we try to fit those distributions to the posterior. And to fit those distribution, we have now created a reverse scale divergence. We are now going to use a reverse scale divergence, which is basically this, that expectation where the z is going to be sampled from the variational distribution, and the thing that is inside is log of qz divided by the posterior, right? And here the goal is that we would want to tune the variational parameters. So this is going to be the variational parameters. I should write this as a variational parameter, not hyperparameters, but variational parameters. Okay, variation parameters, which are nothing but these parameters q of z nu star. Okay, the variation parameters. I will try to tune these variation parameters in such a way that the variational distribution comes closer to the posterior distribution, the target posterior, which I do not know about. But the problem is that all this I understood, and this is exactly the form here. If you try to understand, picturize this in your mind, this entire oval set, this oval set that you see in the purple color, this is a set of your analytically tractable family of variational distribution. Okay, this is an analytically tractable family of variational distributions. And you can think of that, I've already given you an example of a normal distribution, right? So you can think of that all possible normal distributions with a variety of means, with a variety of covariances, all come into this particular set, oval set. And then there is a posterior distribution, which is let's say bimodal or something. It's very arbitrary, you really don't know. And that distribution really doesn't fit into the set. It does not fit into the set, because all this is a set of, let's say, a normal distribution which has only single peak. So it does not really fit into this set. But you can actually make a closest approximation to this posterior distribution. You can make a close approximation to this posterior distribution using some normal distribution, some normal distribution. What is that normal distribution? That normal distribution is probably a normal distribution with parameters nu star. Okay, so let's say you may actually kind of start your optimization with some kind of an initial parameter nu in it, and eventually with some iterations you will actually get to a normal distribution, let's say, with parameters nu star. And that particular distribution is the closest or the best approximation that you can make with your variation family of distribution to the posterior. It is not exactly the same. As I told you, that's a compromise. It will never be exactly the same, but it will be closest. And how do we measure the closeness? We measure it by the KL divergence, right? We measure it by the KL divergence. So the KL divergence is the metric that we use to actually measure that how far or how dissimilar is my posterior distribution from my variational distribution. Sorry, this one is Z given X. Okay. So yeah, I'm using this difference is basically, I'm showing it in an arrow because depends from which side you're going, it will be different. So this is actually basically the KL of Q given T, right? So we use this, or it's all fine. So I hope that you're able to get a picturization of what we're trying to do, how we are trying to optimize. Now I'll tell you that what is the problem as of now. So here we have now said that this is going to be the KL divergence, and we already know that the KL divergence is defined like this for this reverse scale divergence, and we want to be able to evaluate this objective function so that we can use it to minimize the function, minimize the reverse scale divergence. The problem here is that this bottom term, which is the posterior probability of z given x, is now not known. We know that that is not known. For sure, we know that that is not known. But what is really the problem is that, okay, it is not known is one problem, but the expression for it is like this. This is coming from the Bayesian inference. We already have seen this. That probability of z given x is equal to probability z and x, the joint distribution, divided by the evidence. The problem here is the evidence. This evidence is actually coming and creating a nuisance. This evidence we cannot calculate. So let's try to find a way to calculate or to avoid this evidence altogether. So what we'll do now is that we will try to rewrite. We'll try to rewrite this scale divergence in a way that does not involve this evidence. If we can do that, then that will be great, because then we will be able to calculate our objective function. Right now, the objective function is this scale divergence, this reverse scale divergence. But the problem here is that this particular posterior, which is there in this denominator here, is actually having this evidence term, which I really don't want to touch. I just want to get rid of this. How can we do this? So that is what I'll do now. So let me just remove this. Just try to rederive. Okay. So this is an important step. Actually, this is the most important step in understanding variational distributions, variation inference. So KL, which I'm going to now represent as KLD, is expected value of with respect to Q of Z. Reverse scale actually is nothing but log of Q of Z divided by the unknown posterior probability of Z given X. Okay. And now what I'm going to do is that I'm going to use this small trick of log of A over B is equals to log of A minus log of B, right? That's a small trick. And expectation is a linear operator. So it can actually easily take all of these and separate it. So I'm going to use this. I'm going to say log of Q of Z minus expected value with respect to Q of Z log of P of Z given X. Okay. And that is equals to expected value of Q of Z. I'll leave this as it is minus here I will write out the evidence term, because this is where actually I can write out the evidence term. This one here, probability of Z given X is actually equals to probability of, we have already seen this, Z comma X divided by the evidence term, the nuisance term. We'll try to now get rid of the nuisance term in some way. So I'm going to write this here as log of P of Z given X, Z comma X divided by P of X. Okay. So now, actually, let me have it. Yeah, let me just keep it like this. So now we can see that again, using this same idea of log A over B, we have log A over B here again, right? Log A over B, and I can separate it. And you'll see that what turns out that the KLD is equals to the expectation of log of QZ, expectation of log of P of joint distribution of Z and X, and the expectation of this. Now we'll see that all these expectations are with respect to the probability distribution Q of Z, the analytical distribution, our analytical distribution. So that is all good because that's in our hands. How we can actually evaluate these expectations if we have the values of these. So this one I have value, great. This one also I know, but what about this one, log of Px? I do not know this. I do not know this and I do not know how to calculate it. I want to get rid of it. All that I know about this evidence term P of X is that it is a constant. What is the value of the constant? I do not know, but I know that it is a constant, right? Somehow I have to get rid of that constant. Well, it turns out that we are actually solving an optimization problem where it's a constant, so we can actually remove it. How? Well, here you see that this expected value with respect to Q of X, if I kind of remove these, this is an expected value with respect to Q of Z, whereas here things in the inside the bracket, there is nothing which is actually a function of Z. There is no function of Z inside the bracket, which means that I can write that expected value of log of this thing, this entire thing here, now I'm going to rewrite here. And you'll see that this value, this particular value that I'm actually now highlighting is turning out to be a constant. How? Why is it turning out to be a constant? Because the expected value of the log of P of X, if you look into this, is nothing but an integral. This is an integral, okay? That's an integral. And the integral is basically for this function, log of P of X, with respect to what? With respect to Q of Z of X, with respect to QZ of X, right? Now you see that log of P of X, this is an integration with respect to Z, right? This is an integration with respect to Z, right? Whereas this is a function which is actually a function of X, right? It's much like saying this is like y of dx. You can easily take out y and just integrate over dx because y is not a function of x. If y happens to be a function of x, that's a different case. But if y is a different variable, then it's just a constant. Similarly here x is actually, here you see that this thing is entirely a function of x and not a function of z. Therefore, it comes out of the integral. And what is the integral of a probability density function? The integral of a probability density function over its entire domain is nothing but 1. We know that at any probability density function P of x dx from its minus infinity to plus infinity is equals to 1. That is the definition of a probability density function. So what happens now is that this function turns to be 1, and this comes out as log of p of x, which is nothing but a constant. I know at least, even if I do not know what is the value of p of x, I know this much, that p of x is some value, and that value is a constant. What is that value constant? Whether it is a 5 or 10, I do not know, but I know that's a constant value, right? Now, since it's a constant value, I can now replace this. I can now entirely replace this, right, by some constant, right? By some constant. So what we do now is that this one is becoming our new expression. So KLD, the reverse KLD rather, is actually turning out to be this expression. It is turning out to be this expression, and a constant term. Okay. So earlier we were trying to minimize this. We were trying to minimize this KLD, and we faced the issue that, okay, the KLD has this evidence term which we do not know how to calculate. The value is not known. But now we have shown that whatever is the value, that is not known, but I know that it is a constant value. It's not changing with the Q. So that's a very good news. It's a constant value, which means that the KLD can be actually, I mean, the KLD need not be calculated. What we can do, you can calculate the KLD up to a constant term, and that constant term remains constant, so it does not really affect the optimization. It is always constant, right? It is much like if you are to trying to optimize 5x, 5x square minus 2x plus 5. This 5 is really not important because it's a constant. It doesn't change with your parameter x, right? So that 5 actually you can remove, and you can only optimize for 5x square minus 2x, because the optimization function is a function of x, not that 5. So similarly here, this turns out to be a constant. So therefore, it actually kind of reduces. So what happens now is that we we now take this constant value and bring it to the, we actually take this constant value and bring it to the other side like this. Or slightly different way is that you can actually take this function and bring the KLD to the right hand side, and all of these terms to the left hand side. If you do this, then we actually get a term, something called as evidence lowered bound, or in short, it's called elbow. So you see that I have taken this part here and taken this part here. So log of p of x, which is nothing but, it's called the log evidence. This is the evidence, and the log of this is called the log evidence, minus the KLD, okay, is turning out to be the left hand side term like this, and this term here is called a new term called elbow. Okay, it's called elbow. It stands for evidence lower bound. It's called evidence lower bound. Okay. Now it turns out that earlier we were trying to minimize the KLD. Earlier we were trying to minimize the KLD, or the reverse KLD. Okay. Uh, Now we have found out an evidence lower bound, and we may actually consider trying to maximize this. Why maximize this? Because the KLD here is negative. So if you want to try to minimize the KLD, then it is equivalent to maximizing the elbow, right? Minimizing the KLD is like maximizing the negative of KLD, and here the elbow is actually having a part which is negative of KLD. So elbow is basically a sum of, you can look into this, that here we have already had the decomposition. It is a sum of the negative KLD and a constant term, which is the log model evidence, right? That's what is written here. It is the sum of the negative KLD and the constant log model evidence, and that is actually equals to this entire left hand portion, right? That's entirely the left hand portion. So this is the thing that we need to evaluate. And so now we have a modified objective function, that instead of minimizing the KLD, we will actually consider maximizing the elbow. Instead of minimizing the KLD, we will maximize the elbow, because it is going to be equivalent, because there is only a constant term, and that constant term, whatever its value, it will not affect our calculations. So great. So instead of minimizing our KLD, we are now going to be maximizing our elbow. Now, why the name? You might question that why the name evidence lower bound? Seems like there is some mathematics, there is some lower bound involved. Yes, there is actually some lower bound. You can think of this, that this model evidence is actually a constant. This model evidence here is actually a constant, right? And KLD, as I told you earlier, is always greater than or equal to 0, right? So whenever you have some term which is a constant, and you actually take out something from that term which is positive, you're always going to end up with a value which is lower than this. It is always, this value is always going to be lower than this value. It is always going to be lower than the log model evidence, right? So the log evidence is always going to be higher than the elbow, and therefore we say that the elbow is kind of a lower bound approximation to your log evidence or evidence. Okay, it's a lower bound. It is always less than the log evidence because you're taking out from the log evidence a positive term, and therefore your elbow is always going to be smaller than the log evidence. So that is the a simple intuition. Of course, you can actually look into a more rigorous proof. A rigorous proof is like this, that you can actually look at the log model evidence and then you can actually. Is there a question? Okay, so I'll continue. So you have this log model evidence, I mean log of PR, log of px, and then you can actually show that if you kind of do an integration, you can actually like do this integration like this, that p of x is nothing but as if you had integrated p of x and z over dz. If you integrate this out, you will be only left with p of x. Okay, so that is actually a decomposition here. It is done, and then what you do, you introduce q of z in the numerator and denominator. So effectively they get cancelled out. Effectively they get cancelled out and there is nothing. But you purposely introduce this so that you can tag this particular qz underneath here, and then this particular qz comes here, and you will find that this expression now looks as an expected value. What is the expected value here? It is the expected value of this particular thing with respect to this one. So that is the expectation. So you have now turned this log evidence, starting from this log evidence, you are now turning this to a some kind of an expectation over this, the conditional distribution divided by the variational distribution and the log of it. Now people usually use the Jensen's inequality. What does the Jensen's inequality say? The Jensen's inequality is much like this, that logarithm is actually, we know it's a concave function. What do I mean by that? Well, this is a logarithm shown in the black line. Okay, that's a logarithm shown in the black line. So this is a logarithm. It's a black line, and it is a concave function in the sense that if you were to take 2 points, let's say if you take 2 points here, if you take 2 points and draw a line, okay, you draw a line, then this line will always be below the logarithmic curve. Wherever you draw this line, it will always fall beneath the curve. Okay, therefore it is called a concave function. Similarly, opposite is a convex function. If you have draw a line between any two parameters, right, the line, this line between these two points will always be above the convex function. From there you can actually show that if you have these 2 points, and let's say this point is y2 and this point is y1, okay, this point is y1 and this point is, let's say, y2, and you take these 2 points. So these are 2 points, and you take an average of these 2 points, y1 and y2, and let's say that y1 and y2 average is y naught. Okay, so now you take the values of the logarithm at these 3 points. So you have logarithm of y naught here, which is here, the logarithm of y2 is here, and the logarithm of y1 is here. Now if you will see that the logarithm of y naught, okay, the logarithm of y naught is actually appearing higher than the average value of the logarithm of y1 and y2. Okay, so which means that the log of y1 and y2, which is basically log of y naught, okay, that, which is this value here, is appearing to be higher than if you were to take log of y1, which is this one, log of y2, which is, let's say, this one, take, sum them up and divide by 2, because they appear on the line. So this is the property of a logarithmic or a concave function. And from here you can actually, this is actually a kind of intuitive way of telling the Jensen's inequality, but you can show that by using this, you can show that the logarithm of an expected value of a random variable is actually always greater than or equal to the expected value of the logarithm of that quantity. I'll repeat that once again. The logarithm of the expectation is greater than the expectation of the logarithm. Okay, that is the Jensen's inequality. Now, why do we need to, why I told you about this? Because here we have the logarithm of an expectation. So logarithm of expectation, just like we have it here, right? The logarithm of an expectation is always greater than or equal to the expected value of the logarithm. So from that one, if we use the Jensen's equality, we can say that this logarithm of the expectation is always greater than or equal to the expected value of the logarithm. And the expected value of the logarithm happens to be expected value of q of z and log of this thing, and that is nothing but the elbow. So we have now shown that the elbow is always less than or equal to the log evidence in a very rigorous way. Okay, so that's the rigorous proof. Nonetheless, it is sometimes useful to understand that why is it actually called elbow. So now this elbow also has a very interesting property, in a sense that this elbow, if you actually kind of break it down, this elbow is actually a function of this q of z. As you can see, it's a function of q of z. If you change the q of z, you will actually change the value of the elbow. So therefore the elbow is written as a function of q of z. Okay, now what happens is that this function of q of z, if you actually kind of look into it and you can break it down, so here you have the log. So log of, again, log of a over b is equals to, we know it as log of a minus log of b, right? So here we have again like this, log of a over b. So what we'll do is that we'll take expected, that elbow value is, now we're going to write it as log of a minus log of b. So expected value of log of a, which is log of p of x, z and x, minus expected value of log of b, which is log of q of z, right? And if you do this, you can further take this one out. Further, we can take this one out, because we know that probability of z comma x is also equals to probability of z, probability of, by multiplication rule, x given z and probability of z. We already know this. And this one we actually call the likelihood, and this one we call the prior, right? You can also break it up like this, and you will be able to show that it turns out that this elbow can be decomposed into this part and this part. And if you look into this part here, you will see that this again is nothing but the KL divergence of q with respect to p of z. Earlier we had a KL divergence of qz with respect to pz given x, but now we have pz, which is just the prior. Okay, and the first term here, this term here is called the expected log likelihood. So you have this is the likelihood, this is the log of likelihood, and this is the entire thing is the expected log likelihood. So you have two parts. The elbow over this distribution breaks down into two parts. One, which is the expected log likelihood, minus the KL divergence between the prior and the variational posterior. So this is the variational posterior, right? This is the variational posterior, your approximate posterior, and this is the prior. So what does this actually tell us? It tells us that the elbow is a combination of your data fit and the deviation from your prior. So this is a deviation from your prior. It tells you that this part tells you that you should try to fit the data well, and this part tells you, so the part one tells you to fit the data well, and part two, which is a KL divergence between the variational posterior and the prior, tells you that you should not deviate too much from your prior knowledge. Should not deviate. So it penalizes, and since it penalizes, you have a negative sign here, right? It penalizes. You see that in that way, the elbow acts as a regularizer. It's a regularizing objective function. So this is a, I mean, if you didn't have this part, if you didn't have this portion, then it would, this, your model would try to fit the data as best as possible, also fitting the noise. But here, since because of the scale divergence, it will probably try to pull it from fitting the noise, because it will say that no, don't fit too much. If you fit too much, I'll actually kind of penalize you. So that's the reason the scale divergence between the prior and the variation posterior acts as a regularizer. So that is the idea. So elbow can also be thought as a regularized fit to the data. Okay. So that is one thing. So now let's recap what we have actually established. First, again, I'll recap. We wanted in Bayesian inference, we wanted the posterior probability of z given x, right? But we found that this was a nuisance term, the evidence term, and we said that there is stochastic approximation where we can actually get rid of that evidence term, that is by MCMC methods. We don't want to be using that because they are computationally very slow, can only be done for a few variables of z. Here we are saying that we are going to do deterministic approximate inference, where we use the variational distribution, our own chosen distribution, to approximate the unknown posterior probability distribution pz given x, that is unknown and I do not really know about it, but I have found out a way where I can actually still make my variational distribution closer to the posterior distribution by a very different method. The different method is that we are now going to be maximizing our elbow, and we know that by our calculations from mathematics, we know now that this maximizing the elbow, which is nothing but this expected value of log of the joint probability divided by the variational distribution. If you can do this, then we know for certainly that this maximizing the elbow will minimize my reverse scale divergence. And if I minimize my reverse scale divergence, I know that my analytical posterior, my variational posterior is going to be closer to my target distribution. I have that much of guarantee right now, right? So now with this guarantee, we now try to tune the parameters of this variational distribution, which is this parameter. So we are now going to tune the parameter of this variational distribution, which is the variation parameter, so that we can actually get to the point. Now, since this variation inference was actually thought to make life very simple, so when it was first introduced, they also use something called as a mean field approximation. So the idea of mean field approximation is that the idea was that since we are going to do an optimization, nowadays we actually have very many optimization tools. For example, we have gradient descent, we have very many toolboxes which can actually kind of give you like you just put your optimization function and they will actually optimize. There are many methods, numerical optimization methods, that are readily available. But the easier ones, the most easiest way of doing optimization is to actually find out the update rules very in a closed form. Update rules meaning that in every iteration, how do you update your parameters in using a closed form solution, not by using the finding a gradient and tuning it. So closed form, if you are looking at trying to uh, update your parameters in using a closed form expression of a gradient, okay, then the mean field approximation becomes very useful. What is the mean field approximation and why is it used? Well, typically variation inference is done for when the latent space is very large, in the order of more than hundreds. And when it is more than hundreds, the optimization becomes even more simpler if you use factorization of the distributions, meaning that here you have a variational distribution q of z. If you were to kind of, so variation, this is actually nothing but q of z1 comma z2, like this up to zm. If you were to kind of take a distribution of this order, it would actually kind of can make your life a little bit difficult. So here earlier it said that let's use a distribution which is actually kind of independent of each other. So it is like q1 of z1, q2 of z2, like this, multiplied like this with qm of zm. So this is actually called the mean field approximation. Why it is called mean field approximation? Because this idea of taking independent distributions or independent effects is actually coming from the particle interactions in statistical physics. So as such, this mean field, you don't need to understand what is really meant by mean field, except that what we do is that we take the variational distribution and whatever factors it has. So factors meaning that z1 z2, like whatever these components are, you're going to define an independent distribution over all of these components, independent. Okay, so that is the idea of mean field approximation. So here I formally introduce it, that if you have a latent variable z, which is a vector, then each component zj is assumed to be independent of mutually independent. They're independent of each other, meaning that q of z, which is a joint distribution over the joint variational distribution over the latent variable z vector, but here you're writing it as individual. You're all of them are you're making independent of each other, and therefore you can write it as a product. So this pi that you see, this pi here that I write, big pi, it is actually a symbol for multiplication. Product. I will write it as product. Okay. So the index go from j equals to 1 to m. So z is actually a vector of size m. Okay. So therefore you have these many factors which are multiplied. And what happens is that the you will actually get closed form solutions for this. That is great. But what will you lose out is that, let's say if your exact posterior is like this, if your exact posterior over a 2D, let's say you have two variables z1 and z2, and in the 2D the contour is looking like this. This contour shows that it is actually also correlated, and since it is correlated, since the two variables z1 and z2 are correlated, so therefore you are actually having this kind of a tilt at an angle. But if you use the idea that you're going to be using the mean field approximation, meaning that your distribution, your variational distributions are all independent of each other. If they're independent of each other, then this correlation between Z1 and Z2 can never be captured, because you have already assumed that my q of z1 is independent of my q of z2. If they're independent of it, then there is no way you can actually capture the correlation between them, right? And therefore you will end up with a distribution, with a variational distribution, which is likely being a circle, because it is independently capturing the dispersion, the deviation in this axis, and it is independently capturing the deviation in this axis, and therefore it is resulting in a circle. A circle has zero correlation, right? A circle, a cloud will have zero correlation. So if you use a mean field approximation, you can never capture the correlation if you use a mean field approximation. If you are not using a mean field approximation, then of course you can actually capture correlations. But I'll show you that using the mean field approximation, you can actually you can actually do a lot more stuff in a much easier way. What comes easier way? The idea is that you can actually create a algorithm which is called the coordinate ascent variation inference, or in short CAVI algorithm, that uses a mean field variational family. Mean field meaning that all the distributions factorize out, and therefore there are no correlations. They're all independent of each other. There are no correlations between each factors or each coordinate. So coordinate, by coordinate I mean that z is actually a vector which is actually having z1 up to zm, and each of them are called coordinates. So this is actually the first coordinate. Okay, this is the mth coordinate. So what if you actually assume that all of them are independent of each other, each coordinate is independent of each other, then you can use this coordinate ascent variation inference, which uses the mean field variational family, meaning that all of them are factorized independent of each other, and you can actually optimize the elbow, which we now want to optimize iteratively for each coordinate. For each coordinate distribution, you can actually iteratively optimize it while holding all others fixed, right? How can you do it? Well, I'm going to jump directly into the result. The result here is that the optimal jth factorial distribution, the jth variation distribution is like this, that qj star, the optimal distribution qj for the jth coordinate is actually proportional to the exponential of the expected value of the log of this. Now, that's quite a mouthful. Let me explain it step by step. This is just a form. This is the direct form that I'm giving you. So zj is basically the jth component of the latent variable z. So latent variable z is actually a vector. The jth component is zj. Z minus j represents the vector of components of z except the jth component. So you are leaving out the jth component, and whatever is left, that is called z of minus j. And probability of zj given z of minus j is basically the conditional distribution of zj given that all other latent components in the model and all the observations are actually kind of given fixed. Okay, and variational distribution is basically variation distribution like this notation: q of minus j, z of minus j is the variational distribution over the latent variable except that zj component. Okay, so it is effectively the product of all the variational distributions except the jth component distribution. So here it says, this particular formula, it shows that if you want to find out the optimal variational distribution for the jth coordinate, if you want to find the optimal distribution, then the form of that optimal distribution should look like this. And this is only possible to get if you use a mean field approximation. If you do not use a mean field approximation, you will not be able to get an expression like this. And moment you get an expression like this by using a mean field approximation, your updates will become much easier. They will become much cheaper, because now you know how to find out your variational distributions along each coordinate by holding the other coordinates fixed. So the way it happens that you keep one coordinate fixed. So let's say if you choose z1, then all other coordinates are fixed. You actually make a update in z1, then you move to z2. While keeping all other coordinates fixed, you update z2, then you go to z3. Like this, you actually go up to zm. So like this, you actually do iteration across all the coordinates. So this is the expression. Of course, how you actually derive the optimal value. The optimal value is actually derived in a certain fashion. I'll probably not go into the details. I'll share the lecture material with you so that you can go over the details of how you actually achieve this particular expression. In the interest of time, I'm going to skip it, and I'm going to show you that how it actually kind of works. So the Kavi algorithm, it requires the input that you have to provide it the probabilistic model, the joint probabilistic model, probability of Z or Z and X. You have to also provide the data. Then you have to choose your variational distribution. In this case, it is a mean field variational distribution, which means it actually factors out. It's a product of the individual coordinates. And then you initialize your coordinate, you initialize all your variational distributions. And after you have initialized this, then what you can do, look at you can actually kind of track the elbow. You can track the elbow, and to track the elbow, what you do, you basically set your variational distribution as proportional to the exponential of this thing that we have already got. And then using this, you evaluate your elbow. So your qz, once you have your qz, you can actually evaluate the elbow. You can evaluate the elbow. You get a value of elbow for that particular value of q, and then you keep on iterating this until the elbow has not converged. Just like the way we do optimization, we keep on running iterations until we find that there is convergence. We'll actually stop there. Right, the same idea here, but here the only thing is that you have to iterate coordinate by coordinate. So you see that it is running from j equals to 1 to m. So you actually start with the first coordinate, then go to the second, third, fourth, like this mth coordinate. Right, that's the idea. Here is just a small example to show how it works. Here the idea is that you want to actually find out that how many clusters are there, and you want to find out a probabilistic model over these clusters of data that are there. You have to find out the hidden patterns in the data. So you want to find the number of clusters and the cluster densities. So here you have, I believe, 1, 2, 3, 4, 5 clusters. Okay, so you kind of start off like this. You initialize all of these clusters. You may not know all the how many clusters are there. You can also create a distribution over it. So here there is a distribution over the clusters, and also the distribution over the mean of the clusters. Okay, mean and the variance of the clusters. So here you initialize like this, and let's say at the iteration 20 of the Bayesian variational base variation inference, you will see that the clusters are actually forming. So you see that there is one cluster which has formed, in fact not one, two clusters which are formed like this, one cluster which is formed like this, and there are two other clusters like this. Right, so total in 5 clusters. Then you have iteration 28. In iteration 28, the clusters are forming with more clarity. Here iteration 35, more clarity. Iteration 50, quite good clarity. Now you see that these clusters, they actually don't capture the entire data. They capture, you see that because they have used a variational distribution, which is a simpler distribution. In this case, they are Gaussians. They all are capturing these ellipses. They are capturing these ellipses like Gaussians, but they're not exactly capturing. Maybe the actual posterior distribution is not really a Gaussian, but it is a something like this. But it is not able to do that, as I told you, because we are trying to approximate a unknown distribution using some known distribution. Therefore, this kind of thing is happening, right? And if you look at the evidence lower bound with iterations, you see that with iterations, the evidence lower bound is actually kind of increasing. You mind you that evidence lower bound is supposed to increase because we were trying to maximize the elbow, right? And you can, although you see the negative values here, but the negative values are actually decreasing in that as we go higher and higher with the iterations, right? So negative values decreasing means that evidence lower bound is increasing. So this is the idea, and there are some practicalities to it. Just I'll finish up with this practical and I'll stop. The practicalities are that whenever you are doing this mean field variation inference or KAVI, you have to remember that this elbow objective function is non-convex. It is non-convex, okay? So since it is non-convex, it means that if you start at a certain point, then the KAVI algorithm is supposed to converge to a local optimum. It need not be a global optimum because it is non-convex. So it means that this is a non-convex optimization, right? So if you start here, you might get fixated at this local minima. If you start here, if you let's say start here, you may get fixated at this local minima. If you start here, on the other hand, you might get fixated here, or you might get fixated here, right? So it is very important that you understand that the variation inference is very sensitive to the initial point. It is very, very sensitive to the initial point. If you start here, it will get fixed here, here, right? So you have to kind of change your initial point because you are supposed to converge only to a local optima because the elbow is generally non-convex. So you can see that with different kinds of values of initialization, the elbow for that same problem actually has given these kind of results. It has converged here, here, like this. For these are the values of elbow. right? So for different values of initialization, the elbow has gotten a slightly different value, right? But you see that it converges so fast. In 50 seconds, it converges. But you'll see that if in a tutorial session maybe later on, you'll see that when you do the same thing with Hamiltonian Monte Carlo, it will take so long a time. And by that time, like variation inference would have just done in a split of a second, whereas whereas Hamiltonian Monte Carlo might still take few minutes to do it for a small problem, I'm telling. Okay. And then how do you assess convergence? The assessing of convergence will happen in this way, that if the elbow falls below a threshold, then you can actually stop the optimization. Or if you track the relative change in the elbow, if you have elbow for the previous iteration and elbow across the next iteration, and if you find that the relative change in the elbow is actually decreasing, and after some time it is not actually increasing anymore, then you probably see that okay, it has probably converged. Or the other way is that you keep a small validation set. So out of your total full data set, you take out a small data set, and on that one, you calculate what is the average log prediction. The average log prediction meaning this value, the average log fit. So this is the average log fit, which I defined it. Yeah, this one, the average log fit. Okay, you put the value of you actually evaluate this on this small set aside data set and check what is the value that is coming in there. If that value is actually kind of changing, then you can think of that you have not converged yet. But if that has kind of more or less it has got a flat line, then you can say that you are more or less converged. Okay, so that's basically the introduction of a variation inference in trying to obtain a, an approximate solution to the posterior. So now we have actually estimated the posterior, or inferred the posterior in an approximate fashion. It is not accurate, as I told you that here you're actually making an approximation. So therefore, you're turning a problem which was supposed to be stochastic into something which is completely deterministic, and you are doing an optimization, right? You are doing a deterministic optimization. There is nothing random as such in this case. The next thing is that people have now moved on from this coordinate ascent variation inference in the last I would say 5 years. People are now doing a stochastic variation inference SVI, because for massive data sets, even Kavi is actually also not that Kavi is also quite computationally intensive. So you can imagine that MCMC, there is no, I mean, people don't even think about MCMC. Kavi is much faster than MCMC. And even now, in today's date, Kavi is also very computationally expensive. So now people have moved into stochastic variation inference, where they actually calculate gradients of this variational distribution. To find the variational distribution, they use gradients using a small batch of data. Just it is very similar to stochastic gradient descent. Okay, so I'm not going to get into that. So with that, I'll actually stop the lecture. If you have any question, I'll be very happy to answer. Do you have any question? Yes, so if you have any question, I'll be very happy to answer. If not, I think then we'll stop the session. Thank you so much for attending. I hope that you'll be able to take back some of the information and maybe use it, or maybe later on, if you come across variation inference or read a paper or try to apply variation inference, you'll be able to kind of understand uh, some ideas of at least some terms that are commonly used in variation inference. Okay. So we'll end the session here. Thank you so much. I hope to meet with you later again, if possible. And I can share my email. So my email is actually Rajdipn, RAJDIPN @iitt.ac.in. If you have any questions